The tent map is a simple piecewise linear function, one of the classic examples in the study of dynamical systems. Starting at x0 equals 2/25, we use a cobweb diagram to trace the orbit. Each step we move vertically to the tent map, then horizontally to the diagonal. This gives us the next value in the sequence. Plotting each iterate on the x-axis reveals a striking pattern. After exactly 9 steps, the orbit returns to where it started. This makes 2/25 a periodic point of period 9. In fact, any rational starting value under the tent map will always be either periodic or eventually periodic. It will always cycle. Now let us take another rational number, 13/19, from the phase space unit interval. It will be shown that it is eventually periodic point. It means it is not periodic, but one of its orbit point is a periodic point. Starting from 13/19, in the 10th orbit step, we arrive at x1 or 12/19. So 13/19 is eventually periodic, whereas its orbit, point 12/19, is a periodic point of period 9. It confirms that every rational point is either periodic or eventually periodic. So for tent map, the set of periodic points is dense in the unit interval. Now we take an irrational number √3 minus √2 in the phase space unit interval. The orbit behavior change from rational point to irrational point is obvious. Irrational points have infinitely many distinct orbit points. Existence of dense orbit points in each open interval is well established. Those points are definitely irrational numbers. Yet, it is still an open problem to determine whether the orbit of √3 minus √2 is dense or not. This pattern is similar for all irrational numbers. The red orbit dots shown in the video has 200 points. For more such orbit points, it is seen to spread out the entire phase space, suggesting the denseness of the orbit, and yet the problem still an open problem. An expansive dynamical system is one where points that start arbitrarily close together are eventually forced apart. No matter how close 2 points begin, the system will always find a way to separate them beyond a fixed distance, epsilon. In this first visualization, we have 2 points, x and y, starting very close together with an initial distance less than epsilon. Watch as the system iterates. After just 3 applications of the map f, the distance between them exceeds epsilon equals 1.0. In the second visualization, the divergence is more gradual. The points start similarly close, but their paths spread apart more slowly through each iteration. Yet the result is the same. By the third iteration, the separation condition is met. This is the defining property of expansive systems. Eventual separation is guaranteed. A dynamical system is said to be sensitive if there exists a positive constant delta such that for any point x and any neighborhood u containing x, there exists a point y in u and a time n for which the distance between f to the n of x and f to the n of y exceeds delta. To visualize this, consider two nearby points, x and y, both lying within a small neighborhood u. As we apply the map f, their images f of x and f of y begin to diverge. Regardless of how close x and y initially are, sensitivity guarantees that their trajectories will eventually separate by at least delta. Iterating further, after 1, 2, and 3 applications of f, the separation grows. By the third iterate, the distance between f cubed of x and f cubed of y has clearly exceeded the sensitivity constant delta. This is the hallmark of a sensitive dynamical system and the mathematical foundation of what we call chaos.